Well, good afternoon and welcome to this session of our specialist forums. My name is Joseph Marchetti, Joey Marchetti. I work for Energy Recovery. We're working on a unique CO2 energy efficiency solution for transcritical and others, both for refrigeration and potentially other CO2 system applications. So welcome, welcome. Please sit down, make yourself comfortable. So this is the legal jargon that says that don't take what I say and report it out to the general world or whatever. So, do that kind of thing for me. So I really appreciate y'all all showing up to listen a bit about our pressure exchanger technology and energy recovery in general. I will speak a bit about energy recovery. We are a 30-year-old publicly traded corporation based out of the San Francisco area of California. A little bit about, of course, the technology and what we're doing to put that technology into work in CO2 refrigeration systems for energy savings, which, of course, with the rising prices of electricity across the globe, become more and more relevant for every CO2 system that's installed across the world. And then finally, of course, I'll talk a little bit about what our experience has been with regards to CO2 refrigeration and where we've done commercial installations. So a little bit about our company. We were incorporated in 1992. This is our 30-year anniversary of Energy Recovery. Energy Recovery was founded really upon this pressure exchanger technology that I'm going to speak about today. Before I get too much deeper into it, I just want to explain maybe high-level principles of what is a pressure exchanger, because most people say heat exchanger or something else to that effect. So ultimately, if I think of an analog to a heat exchanger, if I have one warm or hot flow of fluid and a cool flow of fluid, I can cross-exchange them in an exchanger and then warm the cool fluid, of course, and cool the warm fluid. And I use that, it's used in multitudes of applications around the world, from oil and gas refining to refrigeration to the radiator in your car, right? The pressure exchanger is if I have a high pressure flow of fluid, a low pressure flow of fluid, I can cross-exchange those within our pressure exchanger in a fluid-to-fluid interaction and boost that low-pressure fluid to a high pressure while I'm either expanding or letting down the high-pressure fluid to a low pressure. So what that does is effectively gives me free pumping or free compression whenever I have a pressure loss across a valve or something like that. So this is what the principle, the PX principle is based off of, and this is really what our company is based off of. We are a publicly traded company on the NASDAQ. You can see our financials and such over there. But what you can see is that our company went public in 2008, has grown to shipping 20,000 units. Now, why am I pointing this out? Because these 20,000 units are very similar to the pressure exchangers that we're using for CO2 refrigeration. So we have a lot of experience with this technology. The other thing to point out is that as of this year, we've now sold 30,000 PXs. Why is that important? Not only are we seeing our stable business line growing, but it accelerating, because people across the world are seeing the value and the need to save energy, save electricity out in the world for whatever industrial process that they have. Energy recovery, its technology makes its money in water desalination. So, the principles, why do I bring this up? Because the principles and the proposition that the PX brings to water desalination is exactly the same principles that go into CO2 refrigeration. So in water desalination, our technology over the course of 30 years has gotten to a point where it reduces the pumping horsepower, the pumping electricity needed in a reverse osmosis desalination plant by 60%. So that's one very important side to the value proposition. But the second important side is if I can reduce my power needed by 60%, if I have 1,000 horsepower of installed pumps and I can drop it down to 400 horsepower of installed pumps, that's a lot of savings up front to offset any cost of our pressure exchanger. And so the payout for the pressure exchanger on the water side of the business is anywhere typically from 6 to 12 months. This is important because, as you know, in refrigeration, heat pumps, and the CO2 world, first cost is extraordinarily important and something we are focusing on as well to make sure that this meets the market where it needs to be met. The last point I'll mention here, that's also reflective into the CO2 side is that when we put our equipment in, it operates for 25 years in a location. Never have to touch it, never have to do maintenance on it. There's no other technology that I know of, and I've been around the turbo machinery world for a little bit now, that has that kind of longevity without needing to be worked on in any way, shape, or form, and operating at full capacity for that amount of time. So as you can see, here's our pressure exchanger for the water desalination world. Now let's talk a little bit about the CO2 world. So this is our pressure exchanger for CO2. Ultimately, the value, what the PX does is exactly the same from a financial perspective, from a environmental perspective as it does on water desalination side. So it reduces the electrical usage of CO2, especially if you look at the estimations and things, the models, our value proposition is extremely high where you're at high subcritical or transcritical operation. And of course, this is where CO2 systems in general struggle in terms of efficiency, right? If I put a refrigeration system in Norway, it's just as cheap as an HFC system to run. If I put it in Texas, where I'm from, you can barely convince somebody that that's a good idea because it becomes so expensive from an energetics perspective to run that CO2 refrigeration system. So of course, the number one thing is energy savings. Number two, because we have really good performance at the high temperature, the high loads, the design points of the rack, arguably I can scale back over the course of time. We can justify scaling back the amount of installed horsepower of compression, potentially the high pressure valve, and other things in the rack to offset the cost of the PX to drive a really short payback. Of course, if you think of other energy efficiency technologies within CO2 refrigeration, another one is that you install the pressure exchanger in the system and its auxiliaries, and there's really no, at least from the PX perspective, we expect it to work just as it does in water desalination. No degradation over time. I don't need water. I don't need oil. This is all process lubricated, so the CO2 lubricates the pressure exchanger and the rotor inside. And so it goes in, it runs, and I don't touch it. That's the end goal. And then finally, as we're ever more and more focused on the environment, on the planet, it does allow for you to meet those ESG goals, your environmental goals, to reduce your CO2 emissions, or indirect CO2 emissions, et cetera. The other thing is because it doesn't use water, oil, et cetera, it's not an additional utility that may be regulated depending on if I'm in a very dry climate or things like that. So to dig a little deeper into the installation side of it and the installed cost, maybe not so much the cost, but the installation. First, I want to just take you through briefly how the PX fits into the system. So if I look here on the left, this is, a traditional system where I have my main compressor train. Of course, I go to my gas cooler, and then I let down the pressure through my expansion valve. Of course, here would typically be a receiver, a flash tank, and then, of course, I pipe the liquid refrigerant out to the store to keep all of my product cold and fresh. For energy efficiencies, oftentimes an adiabatic cooler is used. Of course, that requires water. It is possible that you would also incorporate something like parallel compression, compressing that flash gas up back to the adiabatic cooler pressure. So the pressure exchanger integrates in where I expand the fluid in parallel with the expansion valve. So the PX would generally tie in upstream of the expansion valve, expand the CO2 to the flash tank. And then from there, I have the expansion side taken care of. It acts just like the HPV. Potentially, I can remove that over the course of time. On the other side, I get that free compression by the gas cooler flow pressurizing the low pressure flow coming into the pressure exchanger. And so, of course, then I can grab that flow, whether it's from the medium temperature suction or the main suction header or the flash gas off of the flash tank, push that into the PX, and then the PX raises it to nearly the adiabatic cooler pressure. Over the course of time, and after showing the results over the course of time, it's our expectation that we can reduce that CapEx installation cost of using the PX by potentially removing a valve, not needing a parallel compressor, maybe reducing some of the compression horsepower, And then, of course, also, if I can justify the reduction of the gas cooler, of the adiabatic gas cooler in particular, it's not only an upfront cost that I mitigate, but it's also the long-term cost of all the maintenance of the pads, the water consumption, and things like that. So there's a very large opportunity, a large opportunity for us to install the PX to show the justification for reduction of compression, the removal or reduction of the water consumption in the adiabatic cooler, and ultimately making an overall more efficient, more energy efficient, greener system to deliver to end users and customers alike. And then finally, a little bit about where we've come and where we're going with regards to the pressure exchanger. In this industry, now we're fairly new to the refrigeration industry, but in this industry it becomes very apparent to us that you need to get proof in installations, runtime, showing those numbers. So we have partnered with a rack manufacturer in Europe. We are installed in a supermarket. We've run the PX and shown efficiency improvements of 20% and greater in the warm climate, so 30 Celsius and above. We have an installation currently in Southern California that we're managing, tying into an existing rack in that location. We've started to do our 24-hour runs, and so we're finalizing the commissioning there, showing that we can maintain the gas cooler pressure, just like the high pressure valve would, and run across a wide range of loads. We've shown that pretty clearly in Europe, and we're working to get those data and things flowing here in the United States. Finally, we also have another rack manufacturer in the United States that we're going to be doing an installation towards the end of this year, early next year, also in the United States. And what that does is allows us to start to be integrated in the rack, because the best way for us to maximize the value to rack manufacturer partners and ultimately the end user is to ship from the factory with the rack, the pressure exchanger, the PX, and the technology to be deployed at location. And then, of course, we have a few other commercial deployments, some sales, et cetera, that we've committed, they've committed to us, we've committed to them, that'll be happening in Europe over the next several months. And so we continue to build on that, and ultimately, we'd love to do that with you. If you are an end user, a rack OEM, or a rack manufacturer, we'd love for you to come by our booth to get a little bit more deeply into the technical details, to show some of the data points and the value there. So please come by and visit us in booth 7A, number 226. And I think with that, I'll open it up for questions, if anyone has questions. Yes, sir. Did you have a question? Oh, okay. Is there any questions about integration, tie-in, anything like that? All right. Please. That's a great question. No, that's a great question. So the current pressure exchanger is rated for a 60 to 150 kilowatt cooling load refrigeration system. At this point, we have one model to service them all. One thing that's very important about the pressure exchanger that makes it unique is that, so you can see here in the model, I've got a small electric motor here. So the maximum rated consumption is about 0.6 kilowatts. This motor allows me to control the speed of the rotor within the pressure exchanger. And what that does is allows us to control the gas cooler pressure stably. So I think of it a bit like a stepper motor and a valve, that if I speed the unit up, I get more flow. If I slow the unit down, I get less flow. So as of now, the unit is rated for anywhere from 200 to 1600 rotations per minute. So that's about an 8-to-1 ratio. Now, I'm not going to say that scales linearly, but that gives you an idea of the amount of turndown we have to address quite a wide range of system loads and system sizes with the current model size. So we can hit a lot with the current size. With that said, it's certainly in our development plans and discussions that we've had internally that within the same housing, within the same hardware, I can change the rotor. The rotor is the heart of the pressure exchanger, and it controls how much flow I have to coming in and out of the pressure exchanger. So by changing the duct sizes of the rotor, I can have various ranges that I can apply to lower, of course, our lower end of size that we can be addressing, as well as raise the upper size. right? Because as we can raise the upper limit, that gives us more applicability to industrial racks and things like that. Of course, if I can reduce the size on the lower limit, that gives me more openness to things like a small condensing unit, smaller size racks, etc. So good. Thank you for the question. Appreciate it. Anything else? Please. How to control? Yeah, great question. Okay, so for this one, I'm actually going to take us. Please come by the booth if you're interested. I have much more in-depth diagrams and things like that is available to us. But ultimately, the pressure exchanger ties in right here, which is going to be my gas cooler outlet. So with the pressure exchanger, what the main control variable is the gas cooler pressure, just like it would be for my high pressure valve, right? So what we do is we either take the pressure from the high pressure valve, and then we control the speed of the pressure exchanger as I would the valve. So it's a simple PID control to maintain the gas cooler pressure at the appropriate pressure, in the system. And then I just speed up and slow down to ensure that that is held stable. So it's a single input pressure, single output speed to maintain that pressure. Does that answer the question? Okay, good, very good. Anything else? All right. I've got 3 minutes, so by all means, please come by and visit us. Visit us at our booth. We're in Hall 7A, booth 226. And so I'll be over there. Of course, if you want to give me a phone call or ring, even though I'm from Texas, my phone does work so far over here. So give me a phone call, text message, et cetera, at any time, and we'll be happy to have a conversation with you about the technology. All right. I appreciate your time. Thank you so much.